All right,
Hello.
we're live. Hello, Jesse. Welcome back to the show after 1 week of hiatus.
Welcome back yourself.
Thank you. Thank you.
So, what has the Neptune team been up to?
Well, we're focusing on making Triton VM faster. We have a recursive verifier now. In fact, we have two recursive verifiers. One that was compiled down from a subset of Rust. The other one was written by hand entirely. And this the exercise in which we write it by hand has yielded some fruits. A bunch of optimizations were discovered and can now be applied, but we still have a long way to go to make it uh, practicable on average computing machinery.
And you indicated before we started recording that you'd like to talk about virtual machines. So maybe we can start with just the introduction for the layman. What is a virtual machine?
A virtual machine is a simulation of a computer by a computer. So you have a laptop which might be what you're running, what you're seeing this video on right now, or a desktop computer, and that desktop computer is going to simulate what another computer would output based on some inputs. And the nice thing is that the simulated computer, it can have a different architecture from the host machine. And so the simulated computer, I think Java was the first language and virtual machine to achieve this. The selling point is that every Java virtual machine is identical. And so it doesn't matter if I run the Java virtual machine on my laptop or on my smartphone or on my iWatch. They're all running exactly the same machine. And if I run a program on those machines, they're going to behave in exactly the same way. Whereas otherwise, I might get different behavior based on which hardware I'm running the program on. And
Okay.
that's really useful for blockchains because the whole point of a blockchain is that every participant ends up agreeing on the new state, which comes about as a result of updating the previous state with some logic. And so, in addition to agreeing on the data, they actually have to agree on the logic itself. And that's very difficult to do if the hardware that's performing those logical steps is different from client to client or from participant to participant. And the way to get around that is to make sure that every participant in the blockchain is running a virtual machine, which is then identical across all the participants.
And is the virtual machine itself, let's say, on the blockchain?
I'm not sure whether you can use prepositions like on by analogy or by metaphor to make something meaningful. It, in the same sense that the blockchain is on the internet, yes. Is the blockchain on the internet?
But is
Maybe.
I guess my question is more, and I guess it reveals a gap in my understanding that's probably shared by many. But what I mean is this virtual computer something that you use to let's say parse the logic and then store something on the blockchain, or is it something that actually sort of all the parts involved are bits that you can find on the blockchain?
I'd say the first comes closer, but it's and it, the first thing you described, where it's logic that lives on the host machine and it parses data and the output is then stored on the blockchain, that comes closer. But in some cases, and Ethereum is probably the prime example here. it's not entirely client side. The idea for Ethereum is that the virtual machine has memory, and well, everybody stores, or every full node rather, stores a complete replication of that memory. And in order to access that memory, you run a smart contract, which the Ethereum virtual machine allows you to do because you pay gas. And so the Ethereum virtual machine in that sense is similar to an operating system that you ask for an allocation of memory and some CPU time in order to run your program, which would be a smart contract. And so Ethereum does not qualify as entirely client side, because it's the virtual machine is coming out as an emergent phenomenon of all the participants in the network.
Okay, so contrast that with Neptune's architecture.
In Neptune, the virtual machine has no conception of what lives on the blockchain. It only knows the inputs, and the inputs are typically commitments, and the commitment can unfold to a very, very large state, and you run everything locally on your host on the client machine, on the host machine, and you produce a proof of correct execution of this virtual machine execution, and you upload that proof to the blockchain. And so, firstly, there's no global memory, no global. Well, there's global state, but the global state does not deal with memory per se. And so the memory does not need to be replicated. The thing that does need to be replicated is these commitments to smart contract states and amounts, I guess, also. I'd say where the Ethereum virtual machine is similar to an operating system, which you ask for time and memory to run your program, the Triton virtual machine, which is what we use in Neptune, is more similar to just a program. It's there, it takes an input, it produces an output, except in addition to the output, it produces a proof, and you use the proof to communicate with the Neptune network.
But so why don't you have what Ethereum solves with memory? Do you not have the same need because of the architecture? Why is it that you don't need memory?
This is a good question, because you could argue that the thing that Ethereum solves with its memory architecture is data availability. The fact that every full node on the Ethereum network replicates this memory makes sure that that memory is always available whenever you need it. And that takes a very big complication off the plate of smart contract developers, who don't need to manage their own memory anymore because it's there. It's just there for free, basically for free. I think that architecture certainly has contributed to the rapid rise in popularity of Ethereum, and so we're sacrificing that to some extent. And one of the reasons why we're sacrificing that is because it doesn't really scale. Because if you have 1,000, 10,000, 100,000 different protocol participants, and each of them want a piece of state and they want to interact with each other's state, you get an entire spaghetti mess, which is in part of the reason why it's so difficult to run an Ethereum full node. In Neptune's model, if you and I run a smart contract, then you and I need to make sure that you and I both have full view on the state of that smart contract, and we are not allowed to burden anyone else with storing that data. And so, if you and I both go offline and our houses are burned down, and we lose the data, then it's gone. The blockchain does not record a spare copy of our blockchain state. But in exchange, it's much more scalable, because if you have 10,000 people running smart contracts, but they're all local smart contracts in small circles, well, they can solve their own communication problems off band, and the amount of information that needs to reach the blockchain itself is much smaller.
Can you make this a bit more practical? Like, can you describe an example where, let's say, if you were to implement this with Ethereum, this is what you would put in memory. If you were to implement this with Neptune, this is how it would look like. Sorry to put you on the spot.
Okay, let's do an escrow system, like say I'm renting a room from you, and we want to put the deposit in an escrow so that you can't just spend it willy-nilly. I can't just spend it willy-nilly. If you and I agree that the escrow should go back, or that it should go to you, then we both sign off on that, and that's fine. But in the worst case, you want me to pay for damages that I deny having made, and in that case, we need to go to an arbitrator. And so in the escrow system, we have a second spending policy whereby whereby the public key of the arbitrator is hard-coded. And so in order to produce this smart contract to begin with, we create a new page in memory where the smart contract lives. It's in the end code, and this memory is, speaking in the Ethereum case now, this memory is replicated by every participant in the network. And by the way, they have insight into the current state of the smart contract. And so they will be able to tell if an arbitrator was involved in releasing the escrow or not. It doesn't need to be a very large program, but if you have 10,000 tenants and 1,000 landlords, the number of contracts stacks up. Now, compared to Neptune, it's very different in Neptune, because a escrow contract is just another UTXO with a couple of spending conditions, but the UTXO looks like just any UTXO. It doesn't even take more data to store. It's just, instead of a coin, it's actually a coin with very particular spending policies. And you don't see the fact that those spending policies are different. You don't even see the amount. And when one of the spending policies are activated, it's just an expenditure from the point of view of the network. It's just a coin being traded, like coins are traded.
What would the policy be, though, in this case?
Well, either you and I agree that the deposit goes back to the tenant, or distributed in accordance with a fair distribution to the tenant and landlord.
But that part's not visible, though.
That part is not visible. So if you and I agree, then we both sign off, and that signature activates the first spending policy. But that signature is still hidden behind a zero-knowledge proof that hides the fact that the first spending policy was used. And so the rest of the Neptune network still doesn't even know which spending policy released the coin, if they were to know somehow that it was an escrow coin, which they don't.
So what does the network see? Just two UTXOs or what?
Two UTXOs and the transaction. And in fact, the transaction doesn't even link those two UTXOs.
But I thought, what was a UTXO again? Is where the coin go, where the money goes? No.
Technically,
Which addresses?
UTXOs, it stands for unspent transaction output, but you can think of it as a coin. And oftentimes we also use it in the sense of spent transaction outputs. It's the edge connecting two transactions. It's a coin in between two trades. And so
Okay.
you can think of the analogy of the coins in your purse. That would be the UTXOs that you own. And
Gotcha.
by analogy, the escrow UTXO would be a coin in the vault with a trusted escrow agent.
But wouldn't you have two transactions going into the escrow and then one coming out, or I guess two coming out when everything's concluded?
I guess you would, but the privacy layer even obfuscates this information from the external viewer.
And so this information, the public key of the arbitrator, this also needs to be processed somehow. So, but this happens sort of off chain in Triton. Talk about that a bit.
Exactly. So let's continue the example. You want me to pay for damages, which I decline having made. And so we go to an arbitrator. I'm in bad luck. The arbitrator agrees with you. And so what you guys need to do is you need to produce a proof of, proof of correct verification of your signature and the arbitrator's signature. And you can do that by running Triton VM. And you can do that on your computer, and then you upload to the blockchain a transaction that uses this proof to unlock the UTXO.
I think I'm starting to get an inkling of of how that works. So when the nodes in the network, when they see this new transaction, they can verify, okay, this is a correct transaction, correct computation, because the proof is also provided.
Yes.
And contained within that, like that could only happen if I'm struggling to understand is where is the initial logic. I guess that's in the first proof, that sort of when you publish the escrow or not.
Well, the spending policies only release coins, or rather, the proofs only release coins. The spending policies lock them up. So, in total, there are 3 transactions. One transaction is where I spend money into a UTXO, which is then the escrow UTXO. The second transaction is where you spend money. Well, I guess if you're the landlord, you don't put money in escrow. So there are only 2.
Where's the escrow policy? Where does that get defined?
When I make the transaction, I pay into a UTXO that has a given lock script. This lock script determines how it can be spent, and I show you what that lock script looks like. And it looks like either you and I agree, or the arbitrator and you or I agree to spend it.
But so this is all off chain. This is before anything goes on chain.
This is all off chain. What goes on chain is the hash of the lock script.
But how do I show you a lock script?
I show you the lock script, and lock script is just a computer program. So I show you the source, and you hash it.
Instead of okay, so instead of, let's say, in the Ethereum ecosystem, I might publish a smart contract. You could view that on chain. Be like, okay, that looks correct. If I put money here, this blocks, etc. But here, that step happens before it goes on chain.
Yes. So you have to agree. This lock script looks good to me before I'm going to send money there, because if you don't agree, then I'm just going to lock up money in the hope that you're going to help me unlock it.
Okay, it sounds like there's almost like another layer, or perhaps there's more emphasis on the off-chain layer than I'm used to in. Okay.
Absolutely, and this is a conscious choice. We're making it much more difficult for smart contract developers, but what you get in return is a better scalability, because users who don't care about our escrow agreement are not required to store the data, not required to process the state update logic.
So it's scripted in what? Let's talk about that. What is it scripted in?
It's scripted in Triton Assembler, which is the native instruction set architecture that Triton VM can produce proofs for.
Okay, and we talked about this offline a bit. That's analogous to EVM. Sort of, what is it in Ethereum?
I think it's EVM bytecode.
EVM bytecode.
Yeah. Yes, it is. But with the added context that EVM often also denotes the operating system that you ask for permission to run your program and ask for memory allocation and so on, which just does not happen in Triton. In Triton, it's just a program. But yes, there is an instruction set in both cases, and in fact, those instruction sets are different.
I'm just trying to work back to what the user experiences are going to be. So developers don't typically code in assembler. They code in a higher level language that compiles down to assembler. So how would that work with Neptune? Is that part been worked on yet? Thoughts?
There's no restriction per se for compiling from higher languages down to Triton Assembler. We have a compiler from a subset of Rust. So basically you annotate types everywhere and you use while loops instead of for loops, but otherwise it's very similar to Rust. And you hit the compile button and the compiler spits out TASM code. TASM being Triton Assembler.
And the assembler code, I'm assuming, is not super easy to read. Is that correct?
I have no problem reading it.
So you code in Triton?
Yeah, at the start of this conversation, I said we have a handwritten verifier now.
Okay, which is hand-coded in Triton Assembler. Okay.
But it takes some getting used to, and not all programmers like doing that.
Yeah. Okay. Which reminds me of something else that I mentioned offline is that Ethereum was hailed by some for the controversial choice that they made with Solidity, that it was like technically it was questionable, perhaps even awkward, but in terms of it was a good choice in terms of adoption. So goes the argument. because it's so similar to JavaScript, and that allowed a lot of developers to jump in without much of a barrier. Any thoughts on that?
I think JavaScript and Solidity are distractions. The real technological innovation that Ethereum brought to the table was the EVM, and Solidity is just one out of many high-level languages that can compile to EVM. In fact, I'm sure there were other higher-level languages beyond Solidity, and Solidity won out precisely because it tapped into the largest pool of developers that have a small learning curve, which is the pool of JavaScript developers.
So how do you imagine this plays out for Neptune? You guys are focusing on Triton assembler, but the way I understand it, it's theoretically possible to for a higher abstraction to be built on top of that, or to be used on top of that compiles down to Triton assembler. Is this something you would expect to happen, or something you guys want to push yourselves, or am I talking too far in the future?
Not at all. We expect that to happen. We are fans of Rust. Rust is an excellent language. It has some drawbacks, but we don't think any of the drawbacks that Rust has will feature as drawbacks in a pipeline ending up in smart contracts on top of Neptune. So we'll be focusing on Rust and developing the compiler and making it more feature complete. That said, if other people want to develop a compiler from another language, higher level language, down to Triton assembler, we would be very happy about that and see what we can do to support that effort.
And so my mind is going back to what you said about the memory that you use in when you program on Ethereum. Are there any other trade-offs that you're making? Because what you mentioned was that for the developers it might be a bit more difficult because you're asking them to jump through a hoop where they cannot just put it there in memory. Are there any other trade-offs that are being made
you're
here?
putting me on the spot here, because I'm sure there are other trade-offs, but I can't think beyond the main one. Yeah, no. Next question.
Okay, and in terms of like in other conversations we had, you hinted at that Ethereum has. I'm sorry that I keep focusing on Ethereum, but it's just one of the main other sort of smart contract platforms out there. So I'm a bit familiar with the ecosystem, so it's a logical target. But you hinted at there being like an issue basically with getting clogged because there's just so much state to take into account. And so you guys are definitely going for a much leaner approach.
Absolutely correct.
I guess it leads to a similar question. So again, putting you on the spot, but like, are there certain types of smart contracts that would be, let's say, much easier to, or maybe not even smart contracts, maybe we leave it even broader, but like, are there things that you can build that would be much easier to build on Ethereum versus are there things that to build that would be much easier on Neptune?
Absolutely. I'd say Neptune is a smart contract platform of choice for anything that involves privacy. But there are use cases where privacy is not as important as the ability to aggregate across many participants. I think the typical example is an automatic market maker or even an order book where you assemble a whole bunch, collect a whole bunch of trades from various participants and you calculate the market clearing price and then execute all the trades that satisfy that market clearing price and pocket the difference. And all the trades that don't satisfy the market clearing price remain in the queue. That sort of thing is rather difficult to do on Neptune because, well, you have a lot of participants to keep track of, or to onboard onto your overlay protocol. Because once they install Neptune, that still doesn't mean that they speak your overlay protocol. Assuming, for instance, that it's an exchange, a decentralized exchange. They'll still need to install some kind of plugin that speaks with their local installation of the Neptune client in order to participate in this decentralized exchange. And they can do that, but it's an extra barrier towards.
Why? I don't understand.
Why do they need to do that? Because Neptune, the protocol, has no conception of which smart contracts live on it. We're just providing the platform. What you build on top of it, that's up to you. And so if you want to build a decentralized exchange, go for it. But you'll need to find a way to distribute your software. And unless you distribute it widely, you're not going to benefit from the economy of scale that you need to make an exchange profitable.
So this again goes to that larger emphasis on that off-chain layer, the coordination of that automatic market maker that would need to happen within that layer, which you're basically saying you're not the only infrastructure that you offer is the transactions.
Exactly.
Interesting. Yeah, that's a different approach for sure. It kind of is reminiscent of the Bitcoin approach. Like, no, we're not going to do anything besides basic transactions.
Yes, agreed.
Okay, cool. You want to mention your presentation?
Oh yeah, I was at ZK Summit last week, and I gave a presentation on the topic of virtual machines. In fact, but in this case, it was not just a zero-knowledge virtual machine, but in fact a zero-knowledge virtual machine where the registers can assume values from a polynomial ring, where they usually only assume values from the field. So basically what that means is that if you have a zero-knowledge virtual machine, you prove the correct evolution of a state, which consists of a bunch of registers, and those bunch of registers contain numbers. And in order to make the zero-knowledge maths work, those numbers have to come from a finite field. So you can think of the integers modulo some large enough prime number. And what my presentation was about was saying, hey, there's a way to expand the range of values that these registers can take without sacrificing the ability of the proof system to still prove the correct evolution of this state of registers. In fact, you can populate these registers with polynomials, and then you get single instruction, multiple data instructions basically for free, and a bunch of other cool applications. And yeah, there is a way to arithmetize it, and you don't sacrifice the ability of the proof system to prove the correct evolution, which was the what is it? The main point to begin with. Did I drop any jargon terms
you
that
lost
that you
me
would
at
like
at registries.
registers?
Registers. No, but I think that'd be too much to try and peel that onion all the way to its core here. But I hope it was well received.
I got some enthusiastic feedback afterwards, but I should also say that in the middle of the talk, quite a few members of the audience headed for the exit. So I don't.
I would not have mentioned that on the podcast.
I wanted to make you feel better.
Okay. Mission accomplished. All right. Shall we
I think that's a good place
wrap
to wrap up. Thanks, Jesse. Take care.
All right. Thanks, Alan. Good luck and take care.